All right, hello, welcome to lecture 12. So this is a bit of a filler lecture because we have a bit of time. So remember that we're going to have a midterm on Wednesday, and make sure you're looking at all the topics. It's all the same as last midterm, of course. Please watch this review video, and I'll also put that on our lecture page for today, next to our current video, the one that you're watching right now. So yeah, that is that. And I just want to thank all of you who asked some questions, because this is something that I want to do now. So if you come to the course homepage and you click this top link, every week before class, as long as you get your questions in by 7 p.m. Each Friday, I'll make this page ready for the next week, and you can ask a bunch of questions, and hopefully I can get to most of them. So today we only have 3. Thank you, the 3 people who, or maybe less than 3 people who asked these questions, and let's go ahead and go through them and get them answered for you. So let's see. How about I prioritize them by things that might appear on the midterm, just in case you don't want to watch all of this lecture right now. So I think this one will wait, and we'll maybe do this one first, and technically Labo 5 is not going to be due when I release this video, but I can talk about things a little bit there. How do you make a pointer diagram, how you draw structs, things like that. Okay, so let's talk about passing parameters to functions by reference and by value. All right, also by address. So let's just start typing. So when you call a function, let's say it's called foo, with, I don't know, x, y, and z. Usually, if it's called by value, you have a few options depending on the way the function was set up. So here are your 3 options. If the function was call by value, well, maybe I'll make that bold. If the function was called by value, then x, y, and z, and whatever arguments they are, these are just placeholders, of course, got copied into the first 3 parameters of foo. And so those parameters are separate places in memory. Okay? Something like that for call by value, and I'll draw a diagram in just a second. Let me put both of these, or put all 3 here. It's called by address or called by pointer. We do another thing. And then finally, if it's called by reference, we do a 3rd thing. Oh no. All right, so that's the general idea. Let's fill these in now. So if it's called by address, then x, y, at least one of x, y, and z are most likely pointers, because that's what it means to be called by address. You're passing along addresses of things, which means you're passing along pointers. Or at least some of them are pointers, is what I'm trying to say here, because it wouldn't be called by address if you didn't have any pointers that point to variables that were created in some other function, most likely. They could have potentially been made on this function and that in foo, and you just called foo, but that's a bit of a tricky subject, and it's not usually the case. So most likely these variables that you're passing addresses of when you call foo were made in main, for example. X, y, and z could be pointers to variables created in main. Okay? And then often you're not passing along pointer variables, you're passing along, like you're calling the address of operator itself a lot of the time. Often you will call foo and ampersand x, ampersand y, address of z. if you hadn't already made separate pointer variables. Things like that. So addresses are involved for call by address, and in a call by address function, you are able to change memory of other functions. Memory that belongs to other functions, let's say. Okay? And then if the function was called by reference, the x... how do I want to say this? Because we have to talk about the definition of foo. Foo's parameters are aliases for x, y, and z. Changing the parameters will change the will actually change the variables, the original variables x, y, and z. So that is the idea in a nutshell. Let me show you this with that swap function again. So let's pretend, let's do example 1, swap by value. So this is our first example, and I'm going to draw the stack diagram for that. So again, we have main, and I forget the names of these variables, but bear with me. I think it was like a and b. It could be anything, of course. It started out being like 30 and 40. And then we called the swap function that was call by value. And so we said, inside of main, we said, so dot, 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 dot. We called swap with a and b. And the parameters of swap were x and y, let's say. And, well, if you give a to x, that means we're just copying the variables, because that's what call by value is doing. It's copying its variables into its parameters, the variables that you pass along into its parameters. So now x is set to 30, y is set to 40, and notice that these are separate boxes, separate places in memory, and that's the key. That's the reason that this doesn't swap anything. Because sure, you could make this TMP variable, you can start swapping x and y, things like that, and then y equals 10. So we just swapped x and y, sure, but we didn't touch a and b, because when we called it by value, everything just got copied. The a variable got copied into the x variable that was the parameter of swap, and that didn't really do anything for us down in main. All right, that was swap by value. And now swap by address, or by pointer, it looked a bit different. Because when we called the swap function, now we gave the addresses of a and b. So we said swap ampersand a, ampersand b. And down here in the stack diagram, how about I make up the addresses? So let's pretend that a lives at our favorite address 100, b lives at our other favorite address 104, 30, and 40. And so now when I call swap and I'm passing along the addresses, what allows me to touch a and b are the fact that the x variable and the y variable are declared as int star x, int star y. That's how foo is declared, you know, something like that. It was void, right? No, sorry, it was swap. And so because it takes a pointer, now x has to hold an address. Whose address is it going to hold? The address of a. So it'll hold 100, and then y will hold 104. And now we have this kind of situation going on. And now you can see stark contrast from this function where y and b were completely separate from one another. Now we have this arrow relationship, this pointer relationship between x and a and y and b. And so we can do things like, I don't know, star x equals star y after we've done the right thing to temp and all that. But we can do stuff like this, and it'll touch a, and it'll touch b because the star is dereference, and it means follow the pointer. So after we put, like, I don't know, star y in temp, we can say star x equals star y. Or sorry, we have to put star x in temp, don't we? Then we do that. So we're not actually changing x. We didn't say x equals y. We're changing star x. So go to the location where x is referencing, like its address. What is that address 100? Well, I don't know. Let's go there and find that box and start setting that. Okay, so x is pointing to A, and star x equals star y means go to the place pointed to by A, change that to be the place pointed to by y, the value there. So this is what's happening there. Then we'll say star y, so change this, equals TMP. And then we have this situation going on. So we actually touched A and B, and it was beautiful because of those pointers. Those were involved. And we explicitly gave the addresses of those places that we wanted to change, and we explicitly set up this pointer relationship. So that's swap by address. So we were able to change stuff, which is nice. But the way we called the function looked a bit different. Now we finally have a bit of a combination of the two, swap by reference. And references are kind of like the C++ new cool version of pointers where not as many things can go wrong. So they're a bit simpler than pointers, but underneath the hood, they're implemented using pointers. So again, we have our main function, and now we have swap by reference, A and B. And the beauty of references is you just have to change the type of the swap function, and you can call it the same way. So you'll say something like void swap int reference x, int reference y, and then do your stuff. No dereference is necessary, just the type is different. And then when you call the swap function down in main, you'll say, you'll say swap xy. It's beautiful. So you don't have to say ampersand anywhere. It's just, oh sorry, swap A and B. Did I do the same mistake up here? No. Swap A and B, sorry. Say that down in main, and then A, so x is now a reference to A, and y is now a reference to B after we call that function like that. So that's the idea there. So now we have the swap function. This is by reference now. So x and y, those aren't separate places in memory, like they are both in call by value. X and y are different memory locations from A and B. They're also different places in call by address. X is its own box because it needs to hold an address of the thing that we want it to point to. For swap, though, things get a bit weird because references are aliases. They're just another way of talking about things. So I'm going to do my default way of handling that by using colors for all of the variables that belong to this function. So again, we have TMP up here if you go and look at the code, but now x and y, which are references to A and B, they look like this, kind of. So x, if you say x in temp, you're really talking about the same memory location as A, and if you say, sorry, inside of swap. And if you say y inside of swap, you're really talking about this memory location that holds B. So changing one of those can update the thing. So again, you'll say int TMP equals x, x equals y, y equals TMP. That's your standard swap function, which is now going to set TMP to be x, but okay, x is just A, 30. X equals y, well, all right, that's setting this box, because x is A, to this box. So copy that value there, 40, and now we'll say y equals TMP, which is the same as technically saying b equals TMP, but b doesn't exist up here. We can't talk about b inside of swap. It's a scoping issue. And that's a weird looking y. There we go. So this is the third alternative where you use references to actually change the variables, because with a reference, you're just an alias for some other variable, some other box of memory. There isn't a separate place being made for you like there is in call by value when you're just copying stuff over, and also call by address when you're not copying anything over, but you're setting addresses now. And those addresses point to things, and you can indirectly, through that pointer, change what it's pointing to, the value there. References, it's kind of, in one fell swoop, you are the same place in memory. You're just another name for that place. So I hope that after you digest that, read this up here, and look at the code examples for all these different kinds of swap functions, I hope that helps with this answer. All right, so let me make it bold so that I know that I've talked about it. So the pointer diagram from Lab 05, this is Saturday right now, so I can't give away all the answers because I'll probably release this video tonight. But let's talk about how to draw stuff. How to draw struct memory diagrams. And this is actually quite useful because I'll be talking about this later today anyway. So inside of Lab 05, you have your two cool new structs, your points and your boxes, right? So points, if you have a point and you say, I don't know, point P, 1, 2, something like that. Then let's also make a box. Box B equals, I don't know, 3, 4, and then that's not really a comma. That was supposed to be a brace, but now it looks confusing. There we go. 3, 4, I don't know, 5, 6. And so in memory now, these are not pointers or anything. These are just on the stack places in memory. Let's see what they look like when we draw them now. So P, it's a point. And what is a point but a pretty darn big box that holds its variables? It has an x and a y, right? It has a 1 and a 2, and these are really doubles, so you could say 1.0 and 2.0 if you wanted to. And then box B, I think it goes width then height, right? That's what I'm going to assume that it does. Box B will look like this in memory. It's an even bigger box because it's got to hold a bunch of stuff. It's got to hold first a point, so we have to make something like that and put it in there because a box has a point inside of it. So that's called UL, upper left-hand corner of this box that we're trying to represent, which itself has an x and a y. And now you can see how you can get at stuff. Like, I want this x coordinate. Well, I gotta go through B, I gotta go through UL. I gotta get the x then, which is useful. So that's why we're teaching you how to draw these diagrams. 3, 4, and then we have width and height. I'm just gonna say W and H to save space. 5 and 6. So that's essentially what a point looks like and a box looks like if you draw them like this. Alternatively, we just talked about last lecture, linked lists. And if you remember, we had nodes inside of our linked lists, and I drew the nodes a bit simpler than these. So I just made them kind of look like an array, because this is technically a pseudo-array notation, right? If you'd like to do it that way, you can draw alternatively this point like this. 1.0, 2.0. It's still a point. It has those two things that it needs to have, right? And now B, this is where it's very important about the order in which these things are declared inside the struct. So I assume that the UL was declared first, then the W, then the H. If that's not true, this does not make sense. So for this lab, for this and for the midterm, I'd prefer it if you drew your structs like this. It makes it easier for me to know what you're talking about, because like linked lists, I didn't explicitly ever say, I don't know, 1 arrow 2 arrow 3 nil. I didn't actually write things like, oh, okay, this is data, this is next, because this kind of this kind of way of drawing struct's a simpler way. It saves a lot of writing, but it makes it harder for me to understand what you mean. But it's equally valid. So use whatever one you want. I will trust that you know what you're talking about. So this is the alternative way to talk about P because the X comes first, it's declared first, then the Y comes second. It's kind of like an array. And we'll talk about how it's very, very similar to an array. Now, when you're going to translate this B to this alternative way of writing B, it's got deep down 4 boxes, 4 real places that it's holding actual concrete things. So it's going to have 4 things like that, but this first set of 2 is kind of like bold, right? Because it's holding a point, which is itself a set of 2 boxes. So deep down in memory, it's going to look like this, but it's up to you to recognize the fact that these first two kind of go together because they're a point themselves. Okay, so those are your 2 alternative ways of drawing these things. And if you have pointers to these things now, let me put these in like clouds, alternative clouds. I'd really prefer it if you did it this first way, this more explicit way, so I can double check. Alternatives. Now inside of this lab pointer diagram, what's going on is you have some pointers to things that look like this, don't you? Now, if I had a pointer to P, now I have to start making up addresses. Or you don't have to, but it's nice when you do it. I don't know, let's say this is 108. And if I had pointers to these things, like this is PTR1, this is, I don't know, PTR2. In order to have these pointers, first of all, I want to set it up like this. I want PTR1 to hold 100, PTR2 to hold 108, and so that they point to P and B respectively. In order to write code like this, let's pretend that this continues right here, or maybe up here so I have more space. Whee, that's an error. You'd have to say something like point star PTR1 equals address of P, box star PTR2 equals address of B. All right, so that would set that up. Just remember that the types are very important there. So in your diagram, you're going to have pointers and things that they're pointing to, and you'll also have some other argument variables. So if you could do stuff like this, like, I don't know, if you had you don't have to draw the stack, but as long as you say something like main and like init, I got some variables from main that are relevant. I've got some variables from init that are relevant. Some of them are pointing to other things. Some of them got other stuff that might have been copied. Like that green stuff got copied here, let's say. And maybe this was a struct. This is the kind of diagram that I want to see for Lab 5. I want to know that you know which places, which boxes belong to which functions, when those boxes got copied over, when they got related by a pointer, for example. They're supposed to be coming from the middle. Stuff like that. That's really what I'm looking for Lab 5, and anything that looks like a reasonable diagram with this kind of differentiation is all I need. You don't have to like be super cool and draw these stack diagrams like I've been doing. That's just for explanatory purposes. As long as I know what's in main and what's in this other function, things like that. This won't be exactly like the lab, of course. I think it's got a test function and then an init function, right? You'll have to show the relevant stuff there. But that's the idea, and that's what I'm looking for. I hope that makes sense. Okay, so then finally, do some sort of diagram for nodes and linked lists, and that'll help better understand how they work. Sure. So let's talk about that now. Nodes and linked lists. So remember just the definition of those things, and this is very useful for us. We'll come back to it in just a second. So for nodes, we had struct node. And inside of nodes were data values. We're just putting ints inside for now. You can put whatever you want, though. Int data. And then we need a way, because when you draw a linked list node at least, 1, 2, 3, for example, it needs to know where to get to the next node, and so we use pointers for that. And so the next data element inside of the struct, its type is node star. It's a pointer to some other node somewhere else. Could be null, because it's the end of the list, but it doesn't have to be. And then we package up our nodes inside of a linked list struct, which keeps track of a head and a tail. Okay, so these are the two structs that we use, and so at the end of the day, we want to make a linked list struct which has a head and a tail. I'll write the names here, you don't have to, because I'm using that shorter way of writing structs. So the head will point to the first element of the linked list, and the tail will point to the last element of the linked list. And let's say that this linked list variable, which is represented by this place in memory, belongs to this L variable. We said something like, I don't know, in order to start this all out, let's pretend that we did like this. Here's the stack. Here's the heap. They're separated like that. In order to make this diagram, and I hope that's the kind of answer you want to see here, in order to make this diagram of linked lists, here's the code that we need to do. So inside of main, for example, we start off making L. So we'll say linked list, pointer, L equals new linked list. So that just gave us this L, and it's already pointing to, thanks to this new operation, a brand new shiny place on the heap that is going to hold a head and a tail that we will eventually instantiate. So right now it's just holding random stuff, but we want to make this diagram in code. So let's continue. Let us say now, you could do this a few ways. You can make your nodes, just individual nodes, like 1 equals new node. And honestly, that makes more sense, so let's do it that way. Alternatively, you could say something like L arrow head equals new node. But that gets a little hairy, and I don't want to confuse you. So, all right, so right now, this is what we have. We've got this stuff so far. Let's now work on making this first node and setting up this head pointer. All right, so let's make our 1 node like that. Technically now on the stack, we also have this 1, which points to this first node that we're about to make, but I won't draw that. It's not really necessary, but this is another stack variable, just recognize that. And 1's data equals 1, and its next is going to be something that we haven't quite made yet. You could say 1 arrow next equals new node, but let's just explicitly spell out all of our nodes. And then 2's data equals 2, and then node 3, that's a star, equals new node, and then 3's data, of course, equals 3. And now we can start setting up these next pointers. Don't forget about that one too. So, 1's next. And I encourage you to draw the diagram and watch how it changes as I add a line. 1's next equals 2. So that's the address of the next thing. Then 2's next equals 3. And then 3's next, because 3 is the last thing in this linked list, is the null pointer. To finish it off so that we know when we're looping through this list that we're done. And then finally, we need to set up these head and tail pointers to go to the right places. So we say L's head equals 1, so that's the first node, and then L's tail equals 3, which is the last node. Okay, so that is the code to make this diagram for a linked list. And let me go back to this question. Diagram for nodes and linked lists. So yeah, that's how you go from the code to this exact diagram. And then maybe let me give it just a short example of iterating through a linked list, just to make sure that everything is making enough sense. I'm going to try and copy that, paste it on down, and let's keep it moving. Whee! This is what the fast forward button is for on your end. All right. So, here we go. Well, let's pretend we want to iterate through this list now. Let's pretend we want to do it inside the main function. So we'll start out a loop, right? We'll have to make a iteration variable. I like to say n. And we want to start it off pointing to the first node. So you'll say like n equals L's head, or something like that, right? To start it off pointing right here. That's how you get right there, yeah? So now n is pointing here, and then we'll keep on iterating while n is not null. So it's pointing to an actual place in memory that is not null. Eventually we'll get there. And then we'll do some stuff using that node. You can say like n's data. You can like print it out or do other cool stuff with it. That's completely possible. But eventually, if you're in a while loop, you have to do this explicitly. If you're in a for loop, this is part of your iteration update thing. You'll have to say something like n equals n arrow next. So advance n, please. So it's no longer pointing there. It must now point right there. Okay, that's the idea. And now we can do cool stuff in our new body of the loop. And then again, n points here. After saying n next, do cool stuff with this node. And then finally, n holds null. It points essentially nowhere. At that point, we should stop our loop, and we're done iterating through everything. Okay? So I hope that that was enough information. If it was not, please, I'm going to clear this out for this week. Like, come back on, I guess, even Monday. I'll have this set for next week's questions. Okay? So that's exactly what I want you to use this for. So please come back here, click on this first link, and edit this page. I'll change it around, I'll clear it out, and ask your questions, and hopefully I'll get to most of them. They're only 3 this time, and so I was able to get to all of them. That was great. So those are your questions. Now let me just do some things that I wanted to do just to fill everything up. I don't have a full lecture. There are no slides today. Okay? The first thing that I want to do is talk about Lab 6. That's something that's going to be assigned on Monday. And you'll have to do some stuff with dynamic arrays, and I just want to make sure you remember what those are, because we jumped straight to linked lists. So let me make a new folder for today, cd into it, and let me make a file called dynamic arrays.cpp, and let's just go write some short code to make sure we have a feel for what dynamic arrays are, which are arrays that are created on the heap, by the way. So include stream, oops, main, there you go. All right, so main function. A dynamic array is one that is made on the heap. All right, so the way that you allocate an array on the heap is essentially the same as allocating just a single integer. Assuming this is an array of integers, you'll say int star arr equals new int, but you don't stop there, because this would make a single int on the heap. We want to make an array of them. Okay, so let's make an array of 42 things, let's say. And so this makes an array of 42 ints on the heap, and it gives us back a pointer because the new operator always gives us back a pointer, no matter what. We say new, we're getting back a pointer to something. It gives us back a pointer to the first element of that array. And I don't want that to confuse you, because if you say something like int, I don't know, new int star equals new int, this is a single int on the heap. It's not an array. It's just a pointer to a single int. And that's where things might get a bit confusing for you, and I want to make sure that that doesn't happen. So when you say new, you're getting back a pointer, but when you ask for an array, that pointer represents just the first element of that array, because every array is represented by just a pointer to its first element. So if I could say something like int AR2, this is an array on the stack, by the way, so I could say something like this. And if I ever used AR2 by itself, remember that that is a pointer to its first element. So that's why this should make sense still. But it's just a single pointer. Int star, that's all we get back. It represents the first thing in this array. Whereas this represents the address of that one int that just got made for us on the heap. Okay? So please come to office hours, ask questions about this if that's not making sense, and if the book isn't explaining it well either. All right. So that's that. Remember now to, you can do stuff with your arrays now, of course. You can say ARR 5 equals 7, ARR 5 plus plus, ARR 0 equals 0. Whatever you want to do with your array, but eventually you're going to be done with it, right? So to delete an array on the heap, that's a dynamic array, remember to use delete bracket bracket, because C++ needs to compile away deleting an entire array as opposed to deleting just one integer. And so that's you telling the compiler, I really had an array there when I do it like this. Here, if I say delete new int, that's just saying, go to this address, delete the one thing that's there. Alternatively, if I said this, if I said delete ARR, let me keep that actually. So do that, comment it out. Mistake. This will only delete the first element of ARR, because it's pretending now, if you were to do it like this, that ARR was just a pointer to one single integer on the heap, kind of like this. All right? You got to tell it that no, it's an array. Get rid of all of it, please. Okay? So this isn't going to do anything exciting at all except run and complete, but let's just, for fun, compile it. Yep, it didn't give us any memory errors, so more or less it's correct. All right, so it's dynamic arrays, just to bring them back to your mind. All right, let's see here. Oops. Yes, so I want to go now to a homework that'll be assigned this week. So at the end of the week, we're assigning homework 8. And it's going to be about linked lists, yes. There's this one diagram that is super helpful, and I want you to understand it so that you can do it. All right, so again, remember that memory is just a bunch of addresses, essentially at the byte level, but here we're going by 4 bytes at a time, which is useful for us, and a value that's stored at that address. All right, so we have a big table with addresses and the values stored at that starting address. Okay, your job is use this, understand that there is a list variable that starts right here at this address, draw the diagram for that list by just following around pointers starting there. Or not technically pointers, sorry, by following around the memory that is created around this place. So this is the address of the list variable, and using that, draw a diagram. So with that in mind, let me now go back to this example right here. Actually is perfect. Let's see how much I can do. let me, okay, so it's not important anymore that there's stacks and heaps. It's just all memory at the end of the day. So, and head and tail is not useful for us anymore. All right, so here is our setup. We've done this, right? We wrote code to generate this exact memory arrangement. Now let me start adding addresses, okay? So the first thing that I want you to remember is this is a linked list of integer nodes. So the data is always ints. So, and then we're also assuming a 32-bit machine, which means that all pointers are 4 bytes. So remember, in this class, pointers are 4 bytes. Ints are also 4 bytes, but that's something that's always true. All right, so pointers and ints are both 4 bytes, and let me start making up addresses now. So this is 100. I'm going to do it kind of out of order. So this is 104. This is 48. 112 starting here. This is 120. This is 128. And you'll see why I'm doing that. So what this is saying is at address 100 there's a single box that holds a pointer because the pointer is 4 bytes long. All right, so this is going to take up the memory from address 100 to address 103 to store this one L variable that starts at address 100. Okay, so let me write that. So L is a pointer to a linked list object. It is 4 bytes long. And so it takes up the addresses 100, 101, 102, and 103. It starts, and that's the key. It starts at address 100. And knowing where it starts, is all you need to know. Because then you can just increment by 4 bytes to get some place that is not L anymore. All right, so now if I drew memory, if I drew a diagram for memory, actually, let me fill this in, because L is pointing to this place right here. And when you point to something, you point to the starting address. All right, so this is 120. Now, this is where things get interesting, because this is a linked list object. If I scroll all the way back up, it has a head and it has a tail. Those are 2 separate boxes in memory. That's why we have a box with 2 boxes inside of it. This first box, it's a pointer. The second box, it's a pointer. They're both, they're both 4 bytes. Pointers are 4 bytes, ints are 4 bytes. So this is address 120 for this whole starting thing, but this first box is 120 to 123, and this second box is 124 to 127. Okay, do you see where I'm going with that? That is useful information for us. So likewise, this is 104 to 107. This is 108 to 111. All right, but this whole thing, this node, it starts at address 104, but it takes up 8 bytes because the first data element is an int, takes up 4 bytes. The second data element is the next pointer, which takes up 4 bytes. Okay, let me write that. So a node in a linked list takes up 8 bytes. So the first, so the head at address 104 starts at address 104. That was kind of a tautology. I don't have to say that, but the head starting here, this is the head of the linked list. It lives at address 104. And it has a data element that comes first. Its data element also, let me say it like this, and because its data element is first, that data that data variable lives at address 104 also. So this is kind of like a way of viewing memory. You can go to address 104 and expect to see a node there, in which case you'll find something that takes up 8 bytes. But if you go to address 104, really that's the start of the data element of this linked list. And if you go there expecting to see just an integer, well, you can look at the first 4 bytes and get a real integer. It's no problem. That's what I'm trying to say. So this is, it depends on your point of view. The data lives at address 104, and the next pointer lives starting at address 104. And the next pointer lives starting at address 108. So really right here is address 108. And so this entire node starting at address 104, we always use the starting address of things, but it goes from address 104 all the way to address 111. Okay? That was a lot of words. I hope it makes sense. I'm going to draw this table in a second, don't worry. So really, and these are all saying that this node, this entire thing starts at address 128. This entire node starts at address 112. Okay? So with that in mind, let me now draw the table. Address and value. And the table is using hexadecimal. Here I'm using decimal. So you'll have to convert those things. All right. Technically, you can just leave it as it is. It's not a big deal. So here we have the lowest address, 100. All right. I'm going to go incrementing by 4. So address 100. Really, when you see a table like this that skips immediately to 104, it's really saying, all right, this is address 100 to 103. This is address 104 to 107. But it's all in terms of the starting address. That's all we really care about ever. So on this, it's saying starting at address 8000 and going until 80003, we hold this value in all of those bytes. All right? That's the idea. And that's the starting address. It takes up 4 bytes and it holds that entire value. That's the idea that's going on there. So 108, 112, 116, 120, 124, 128, 132. So now I have my addresses. I know where everything is in terms of its addresses. Let me go to the values now. So if I know that L lives at address 100, so at address 100, I'm going to write the value that lives there. So 120, because it's a pointer. So at address 100, L, it holds the value 120, which is, it happens to be a pointer because L is a pointer. And now at address 120 is the start of a linked list. So this takes up, takes up 8 bytes. So it's the start of a linked list, but at the 4-byte element that lives at address 120, it's just the data value of, or sorry, it's the head of this linked list, because first it goes head, then it goes next. I thought it was a node for a second, sorry. So remember that really in here, it holds the address of the first node, 104. And similar for this one, it holds 112. I hope you see that. And so this one holds 128. This one holds 112. This one holds 0. That is the null pointer. It's the 0 address. Okay, so with that in mind, address 104, what does it hold? It holds this 1 right there. All right. Address 108, remember, all I give you are starting addresses. You know at address 108, it's just the next element of this entire linked list node. All right, it takes up 8 bytes, but each of the individual elements take up 4 bytes. That's the idea. So now at address 108, we hold 128. Then 112, we hold 3. Address 116, what's that? Well, remember, starting at 112, we have the node which means that we have the first four bytes taking data, the second 4 bytes taking a next variable. So really, we just say 112, but we're talking about 8 bytes here, holding 2 different things. So really, address 116, secretly holding 0, even though we don't write 116 usually. 120, 104, 124, 112. 128, 2. 132, secretly right here, holding that next element, 112. And so now, we've made from a diagram an address value table, incrementing by 4 bytes at a time. And your job for this homework is to go the opposite direction. Okay? So you're going from memory, and the starting location for that first linked list variable, the thing that holds a linked list object. It's a pointer to a linked list object, just like this L is right here. You have to use that information. It's like saying that L lives at address 100. Now fill in the draw the diagram from this table. You're going the opposite way. Okay, so I hope that makes sense. And a key thing that we just learned out of this is let me actually make it down here. Structs are kind of like arrays in that they are contiguous. Their data is contiguous in memory. For example, a node has a node takes up exactly 8 bytes. The first 4 holds the data, because that's how we declared it. If we did it in this opposite order with next first, then data, then it would have been different, but I'm just assuming the way that we did it. The first 4 hold the data, and the second 4, the last 4 bytes, hold the next pointer. Okay? So that's why it's enough to say, all right, this is a linked list object. It starts at address 120 because immediately you know structs are packed right next to each other in memory, kind of like arrays. Starting at address 120, we're taking up 8 bytes because we hold 2 things, 2 pointers. And the first 4 bytes hold the head, the second 4 bytes hold the tail. You know that immediately from the definition of a struct. Okay? That is the idea there. So I think that's everything that I wanted to talk about. You should have enough information now to be able to go from a table like this and a starting place that holds starting address for the linked list object to this entire diagram. Oops, it went scrolled for me to that entire diagram. Okay. All right. So with that, let me check my time. So let's go to this. Let's just end a bit early today. So I'll take up only an hour instead of an hour and 20 minutes, let's say. Let me just briefly go over something that I'm going to talk about next time. It's called recursion. And I think you've probably heard about this a little bit in CS8 if you've taken that. I think that that's taught there usually. So recursion. Let me write it big because it's important. The topic of next lecture. So I guess not this week because you have the midterm on Wednesday, but next Monday, assuming you're watching this on Monday, will be dedicated to recursion. So let me just whet your appetite for it because it's one of my favorite topics to teach. So recursion is when you solve a problem in terms of itself. And that's a weird thing to think about, but it's very powerful. So you're finding a smaller version of your current problem inside of that problem. Okay, so it's like those Matryoshka dolls where, all right, here's a small problem. I can use that to solve a bigger problem. Or I guess you start out from the outside, right? So I have this big problem I need to solve, but I can break it down into a smaller problem. And if I just solve that, then I'll be able to solve the bigger one. And then, all right, this is still a big kind of problem, but I can break that one down into a smaller problem and use that to solve that next bigger problem. And then eventually you just break it down into a bite-sized chunk that you can actually solve, and then you can use that to solve the whole thing. That's the idea. But let's talk about some things that are defined in terms of themselves. So you've already learned one in this class, linked lists. They're what are known as recursive types. Which is fun. And the reason you have that is because of this right here. A node is made up of nodes. Isn't that beautiful? So here's my list. 1, 2, 3. This is my biggest list. This is the list that I have initially. But I can split this into the first node, and then here is a smaller list. Do you see that? And I can even split this one right here into its first node and a smaller list. And eventually you can even break it down even further to the empty list is a list, I guess. You can say that. So you can split up a list into smaller lists. Isn't that cool? And then the standard problem that I like to give that lets you think about recursion is the example of factorials. Because everybody knows what those are. So, for example, 3 factorial is 3 times 2 times 1. Yeah, let's say it like that. So, what if I told you that the factorial problem, the problem of calculating the factorial of a number, is recursive? It can be recursive. So that means that you can find a smaller factorial inside of a larger factorial. So because the subproblem in this case, you're finding a smaller version of your current problem. That's called a subproblem inside of that problem. It's all getting this is getting weird and meta, but that's okay. So this means that you can find a smaller factorial inside of a larger factorial. So take a long look at this 3 factorial. See if inside of that factorial you can find yourself a smaller factorial. And assuming that you've done that, notice that you have right here 2 factorial. Isn't that neat? So, the factorial problem can be expressed in this way. If you want to calculate the factorial of the number n, well, that is the same as, here it's like 3 times 2 factorial. Well, that's the same as, well, take that n, multiply it by n minus 1 factorial. So I just gave myself a smaller problem. And a lot of the time, that makes it easier to think about. Eventually, you'll notice that, I mean, if I had like 4 factorial, it's 4 times 3 factorial, which is 3 times 2 factorial, which is 2 times 1 factorial. Oh, but 1 factorial, it's just itself. This is just 1. Eventually, you're going to stop, aren't you? You know the answer to 1 factorial without it doing any further work. So you have this kind of recursive case, and then you have your stopping condition. That's the recursive definition, and you have your stopping condition. Where you say, yes, 1 factorial, immediately 1. That's the answer. So using these 2 together, you can solve for any positive factorial now. So you can just break it down into a smaller factorial, and eventually you'll just multiply it all away into 4 times 3 times 2 times 1. Okay? So, do I want to give code for this right now? Sure. let's go as far as to give some code right now. It'll be fun. Let me make one very small file called fact.cpp, short for factorial, of course. And I'll copy most of this. And let's program our factorial recursively. And don't worry if none of this makes sense right now. We're going to talk about this in detail next time, but I just want to whet your appetite, get you used to this kind of idea of problems inside of themselves. Solving for a factorial in terms of itself here, because we're writing a function, we're about to write a function called int fact, int n, right? It's going to return something. Solving for a factorial, it's in terms of itself here, means calling fact inside of fact. That is the key. That should blow your mind. It's a little weird. That is the point. That is the point of recursion. It makes you think about problems in this way, in terms of smaller subproblems. So we have our recursive definition that we can use most of the time, and then eventually we're going to get down to the smallest stopping condition, which is normally called a base case. And this case is called a recursive case. And I will talk about this in detail next lecture, don't you worry. But I just want to translate this math right here to code because that will make next lecture a lot easier. So, all right, check for stopping condition. And let's try this in terms of something concrete, like cout fact 4. And remember that this definition doesn't really work for negative numbers, so let's have a precondition. Precondition. N is greater than or equal to 1. And then our postcondition. What is true after this function is called? The returned value is n factorial. Okay? So if n is equal to 1, I immediately know how to solve that because we just called fact of 1 in that case. Factorial of 1 is just 1. Return 1. Otherwise, this was our base case, we call it, our stopping condition, and this is our recursive case. And here's how you translate n factorial equals n times n minus 1 factorial. That's all you have to do. Return n times fact n minus 1. Okay, you see how I did that? I'm just calling itself, because n minus 1 factorial in terms of code, it's fact of n minus 1. Multiply that by n, you're home free. All right, so I won't prove to you, I'm not going to draw any diagrams this time because I want you to leave early and study for the midterm. But if I compile this, and I run it, I should see 4 times 3 times 2, which is 12 times 2, which is 24, right? Yeah, and we do. We see it. Fact is doing the right thing, and we've made it solve for factorials in a weird way in terms of itself, because factorial is a recursive problem. You could have also made a loop, but we didn't. We solved it in a different way, in a cool new way. And so this is what we'll come to after the midterm. So good luck on that, and I'll see you on Wednesday if you want to come and ask me any questions while you're taking it. So that's all I have for you today. I'll see you next time.